Yeah, it works with Keynote, so let's see if it works with this. You slideshow. No, it doesn't like it.
That's weird.
I can just go to the next slide.
Yeah, yes. But so you're using Keynote, right, for your presentation?
Yes.
So it actually works for you.
Yeah, for me it does work. Yeah. And the other people can just go next slide, or they can use their own laptop. It's somewhere in preferences. No. Guess I can't. Have you seen the company that makes this water? It's actually hilarious. I actually noticed that they were sort of dragging around this big cart full of boxes with Doctor Who stamped on the side. How are you? How was your trip? Exhausting.
Yeah, so because I'm already traveling since the week. No, I was in Seoul last week.
Oh, you were in Seoul?
Yeah.
How was Seoul?
So there was a NetDev conference.
Was it good?
The conference was pretty nice. The location was really the room where the meeting was really weird. It wasn't Gangnam, so Gangnam was okay. The room was really weird, and it was kind of deja vu because we were with the IETF 1 year ago.
Oh,
also in November,
yeah.
so right. So.
So you were Gangnam Style.
Kind of.
Oh, you want me to sign the blue sheet?
You can start.
Yeah, just start it because there's. What time is it? Oh, we're already. We should have started already. So.
I'm trying to get the job.
What's the matter? I have to click the slides because she doesn't have a thingy. So I'm the personal assistant to the chair. No. I see where you're going. Yeah. No. Well, I want to say yes to that, but I'm negotiating about travel with my company. Yeah, but certainly. Yes. Well, no. Well, so I work. I'm employed full time at Certainly, and they pay for my assistant professor, which is a good deal. But I'm negotiating. I'm fed up. Flying all the way across the world in misery.
So, hello everybody. I think the session started already. Yeah. So, if you could concentrate a little bit here, stop chatting. That would be really nice. I'm a little bit disappointed that there are only so few people, but they might also be in the break, and we have to start. So, welcome to the Maprg session in Singapore. We this time only have a 1.5 hour slot. That's mainly because Dave and I were really lazy. So, by the way, I'm Mia Kuderman. This is not Dave. This is just Roland helping me out because I wasn't able to bring the right adapter for my laptop. And yeah, before we officially start, we also have this note about intellectual property for the IETF that you should be familiar with. We have a mailing list, of course, that you can subscribe to, which doesn't have a lot of traffic, but you are all free to actually generate some traffic there. If you want to announce your fancy measurement work or you have some questions about measurements, please use the mailing list. We have some other logistics here about remote participation and the slides. Of course, this link, if you don't have the slides yet, doesn't help you, but you can click on the link otherwise. And that's our today's agenda. So as I said, we have only 1.5 hour slot this time. And Dave and I actually didn't put a lot of effort into try to get various people from the research community into the room. So we are extremely happy that we have a really nice agenda, and that was mainly people who already know about Maprg and came to us and wanted to present their work. So thank you very much. Next time in London, we will definitely ask for a longer slot again, and we will spread out in the world and try to get interesting things we've seen somewhere into Maprg. So stay tuned there. But anyway, if you have something that you would like to present in London, you can also announce us anytime about it, so we can actually take you into account early on, because I guess the agenda in London will actually be crowded. If you, also 2 announcements. So we had this earlier, that we also give people 5-minute slots if they just want to announce their measurement work, which is like somehow ongoing, or if they have requests to the community. That's our first talk. And then another thing that we would like to kind of keep up is inviting people to give updates on previous talk they gave. So if you already have had a talk in Maprg and you just have some newer data, because data gets old quite quickly, you can easily get a 5-minute slot to just present an update. And that's our second part here. And then we have 4 longer presentations. The first one is on principles on measurement. So it doesn't provide data, but I think that's also hopefully good input for this community. And the other 3 are about measurement data. And that means if there are no other questions, or if there are no questions about the agenda, we start with the first talk. Okay, Klaus.
Just shout next slide if you want me to go.
Yeah, sure.
Yeah, and also thank you to Roland again for having me out, but also to Matt Ford for taking minutes.
Okay, thank you and good afternoon. I'm Klaus Nieminen from Finnish Regulator.
Stand
Okay,
to the
closer
mic.
to the mic. Okay, I'm Klaus Nieminen from Finnish Regulator, and it's nice to be here. Next slide. I'm going to talk to you about the European Measurement Tool Project. So that's based on the net neutrality regulation. I'm not actually going to talk that too much here, but what does that mean? Basically, for the end users, that the end users are able to use and provide applications, that the ISP should basically treat all traffic equally, with few exceptions. And for us, the regulators, we need to, of course, monitor and supervise that the obligations are met. Well, if you're interested more about that, there's another presentation you can check. But I'm actually going to the next slide to see about the basic goal about my draft. So there's an ID available that describes also the basic principles of the regulation. The goal is to give sufficient details for developing the actual measurement metrics. It describes the different use cases, basically for the quality of service performance measurements, but also how to detect the traffic management practices that may in practice affect the quality of service or the availability of certain applications. So for example, throttling or something like that, blocking. And it's really important also to be able to detect if it's the end user environment that actually is making the impact, or is it the ISP who we can blame. So basically, again, my draft is available. And well, next slides, please. Now to the main topic. So the European regulators, we have decided to develop a net neutrality measurement tool. Well, we are just starting the actual tender documents. So we don't have yet anything, any code available. But basically the idea is to have an open source tool that's also possible to be available for the whole industry. And basically we are now targeting for, basically few mandatory measurements, like the quality of service for speed, delay, maybe some net neutrality measurements like the port blocking. And of course, it's a tender, so we are hoping to get also many additional measurements to be available in the first place. So basically, we are targeting to have a tool that's available for the end users. They can run it via browser or app and detect the quality or the how to say, neutrality of the internet access service. So if they're, say, their own ISP is doing something nasty. So basically the tender is going to be launched early next year. The development process is basically next year, and we are hoping to get the tool available early 19. And this is something that I would expect that, well, also the industry would be happy to, well, contribute. I mean, that's our goal, to have you to check what we are doing, check that we are doing things right, and hopefully the tool is also useful for other people than the European regulators. I mean, we try to spread the tool to the market, but I would say that, well, also outside the Europe, that's a tool that hopefully is actually useful. So if we can go to the last slide, and also some background information. So I mean, this presentation doesn't give you that much details. So we have the net neutrality regulatory assessment methodology that basically tells our ideas about how to do the measurements. Well, that's the basis for some of the measurements we are now building. It provides basically now our idea on how to measure speed. That's a bit different than what we're seeing in the industry, because it's really based on the, well, IP packet payload, or basically including also the headers, but we are talking about IP level speed, not anything lower. And also some ideas on how to measure the net neutrality. We don't have that many, how to say, standardized measurements available in the market. And of course, well, this is used for our tool. Then if you are interested in the tool development, we have another document regarding how we have specified the tool. It gives you more idea about what we are targeting for. Basically, it should be available in mobile and fixed. It should enable the end users to make their own measurements and help the NRAs to assess the regulation and how it's implemented. So basically, if you have any comments, questions, please contact me. Well, we are happy to share you some information. So thank you.
Do you have time for a question now? A quick question? So Aaron Falk, Akamai. So it looks like you're building this tool and you're going to share the tool, but are you going to share the data that the tool collects?
Well, basically the tool is really early phase now, but well, maybe we can take that offline. I think it may take some time for me to get you a good answer.
Okay.
Yeah, so read the draft, read the documents, talk to Klaus. You can also use the Maprg mailing list to start a discussion there. Thank you.
Okay, thank you.
So next one is Kyle presenting for Dave Plonker, basically giving an update on his talk on IPv6.
Hello, I'm Kyle Rose. I work at Akamai, not with Dave typically, but I'm interested in his work, and he unfortunately was not able to make it, so I'm giving the presentation for him. You can see here that this is a continuing study of the evolution of the IPv6 internet, specifically looking at the use of the address space. If you want to know more about the methodology involved in this study, you can take a look at these two links. Next slide. So you can see here, this is the blue line here represents the observed IPv6 client addresses on a single day in the Akamai network. So across the 240,000 some servers that we have, that's the total number of observed addresses. Close to 1 billion. Next slide. Yeah, no, that's right. Yeah, that's right. They're animations. Yeah. So that close to a billion number is actually more IPv6 addresses than active IPv4 addresses seen per day. Next slide. And if you look at this over a week, you can see that there are more. Next slide. You can see that there are more active IPv6 addresses seen in a week than exist in the entire IPv4 address space. So it suggests that people are using the IPv6 address space in a much more liberal way, which is good. But it's also interesting, and it reveals that that the v6 internet is being managed in a very different way. Next slide. It's also the case that there are more active /64 prefixes seen in a week than there are total IPv4 addresses seen in a week. Next slide. So this is a count of the total number of ASNs that have v6 connectivity. So it's been creeping upward for the last 3 years. You can see that it's reached about 6,500 now. Next slide. So if we look at the number of clients in each of these networks and do a CDF where we're looking at the proportion of ASNs that have a certain number of clients, that have at least a certain number of clients, then you can see if we restrict that to networks that using the KIP methodology, we have determined have a lower bound of 32 independent clients. You see that there are 824 ASNs. And so this graph and the next graph are limited to only that subset of ASNs. That means that of the 6,500 ASNs that have v6 connectivity, only 824 of them actually have more than 32 simultaneous clients. Next slide. So of the 824, about 40% have more than 1,000 /64s per day. That's what the solid blue line indicates. Next slide. Now, if we zoom into the upper right of the previous chart, sorry, go back for 1 second. If you zoom into the upper right, we're going to use a CCDF to kind of look at what's going on with the networks that have many v6 addresses. So what this chart essentially says is, if you look down in the lower right where it's getting toward the right side of the graph, those are the networks that have at least 10 million client addresses. Next slide. So about 1% of the ASNs in this study, so about 10 ASNs, have more than 10 million daily total /64 prefixes or addresses. That says that there's a ton of concentration in the v6 address space at the moment. But many networks have v6 connectivity, but most of the clients are actually in a small proportion of those networks. Next slide. So per ASN, the maximum lower bound estimate of simultaneously assigned /64 prefixes is about 20 million. Now, if the way that this graph is laid out, this is what the green line is showing you is the number of clients, the number of what we believe to be simultaneously unique clients in a single network. In order to get the total number of clients in the IPv6 internet simultaneously, that's essentially the area under this curve, under the green curve, which is a little bit confusing because the y-axis is logarithmic, but if you were to do that integral, you would get about 110 million clients simultaneously. Next slide. So web-wide simultaneously assigned /64 prefixes are about 110 million. That's based on the KIP methodology, which allows us to put a lower bound on the number of simultaneous clients. It could be higher than this, but this has less bias than looking directly at observed addresses, because observed addresses, there are many more of them potentially, as clients can arbitrarily decide when to add a new privacy address. Next slide. So some of the key takeaways from this are that despite the steady growth in the number of IPv6 capable networks, many seem not to have v6 capable hosts. And it seems like there's a very small proportion where where most of the V6 clients are concentrated. So yeah, small number of networks continue to dominate client counts. So the top 1% of networks have more than 50% of the clients by the lower bound estimates of simultaneous clients. And while most IPv6 clients use temporary privacy addresses, there are millions of V6 clients in some networks that are not using privacy addresses. And this is evident from the study, but not from any of the previous slides. If you go forward 1, 2, keep going. Yeah, stop there. If you look at this slide, you can see, so the big purple block there is Reliance Geo. Note how large that is. This is the observed number of addresses seen per day. Now this includes privacy addresses. Next slide. If you factor out the privacy addresses and look only at simultaneous client IPs, that block gets much smaller, which suggests that they're issuing privacy addresses to their clients, where some of these other networks are not. They become more prominent as they become a larger share of the total number of simultaneous clients. So anyway, that's all that I had. Any questions?
Lorenzo Colletti, you can't issue privacy addresses.
Sorry, that they chose privacy addresses. Some networks are using DHCP to assign addresses and therefore don't allow the clients to choose privacy addresses. I misspoke there.
Right. But like Reliance Jio is a mobile network, doesn't use DHCP. I'm not trying to quibble with your explanation, but I wonder if there's something in the data that you're not seeing. That's why, because on wireline, you'd really expect to see these privacy extensions. So like if you took Comcast, for example, you'd expect to see a big thing there, particularly on wireline or Wi-Fi networks where hosts join and leave frequently. Sometimes they might rev their privacy addresses multiple times. But on a mobile network, at least the implementations I'm aware of, they basically, until you disconnect and reconnect, they keep the same IP address. Mm-hmm. And so it's surprising to me that when you look at the data, you see different addresses.
It's interesting. It's something I'll bring to Dave's attention.
Wes Hardiker, USC. Can you speak to why you chose /64 as your aggregation boundary? Because I think the current recommendation, and my data might be out of date because I don't follow V6 closely enough, but I think isn't a /56 another reasonable choice to study the boundary between where network boundaries are, because you may be aggregating multiple /64s who are actually in the same, technically in the same network, because the /56 is the recommended assignment to networks. Isn't that true?
I'm not sure that I can answer that question. I think I'd have to pass that one to Dave.
Okay. Yeah. Look in the latest RFC that recommends where the block boundaries are, and I think /56 is the recommended.
And part of the KIP methodology is to essentially build subnets that are large enough to have at least a certain number of IPs. But I don't know how that fits in with this study, but there may be something there. Any other questions? Thank you.
Thank you, Kyle. Brian.
So hi, I'm Brian Trammell. I'm going to be talking today about a paper that I wrote with Mark Allman and Rob Beverly that was in ACM CCR this April. This is an adaptation of a presentation that Rob gave to SIGCOMM, focusing on slightly different primitives. So I'm assuming everyone here cares a little bit about network measurement, or they just want to be sitting in a cold room checking their email. So it's fundamental operations, research, protocol design, internet policy development. I mean, this is, you got to measure the network in order to know how it works. But there's basically no support in the stack. There's one explicit measurement function in the IP stack. It's ping, ICMP echo request, and echo reply. Otherwise, what we do is we leverage unintended features like traceroute, or we use brittle hacks like looking at passive TCP loss in RTT. So you have to figure out, what congestion controller you're using in order to be able to figure out exactly how much loss you're seeing, so on and so forth. And then there's inference. I mean, like, so there's a measurement conference that I just came from, IMC, that had a whole track on, here are cool little inferences you can use to take, data series that's unrelated to the thing that you care about and try to figure out, try to tease out, something about the performance of the network or something about the topology of the network, so on and so forth. So this leads to a question, right? Like, so the result is that, like, operationally relevant questions and research relevant questions are hard to answer, right? That's why we have a research group here, because if it were easy, there would be no reason for us all to sit here and say, look at my wonderful results. I just, I ran a program and it dropped out the bottom. Yeah, you can do this. We don't need to have presentations about it. So, like, how do you do routing? It's solve problem BGP, right? What's the capacity or utilization of a link? How do networks interconnect? What AS operates a given router? All of these are things that you have to go back to. There's no explicit functionality in the network for finding these things out. Even things that we think are simple or hard, delay between two hosts, right? Like, I'm going to ping this and I'm going to see what the RTT is. I'm going to divide it by 2. That obviously works. That's the one-way delay. No, not at all. There's path delay, there's host delay, there's asymmetry, there's per protocol traffic differentiation. So your ICMP might not even be going over the same path that the actual traffic is going over. We'd like to know what the endpoints are in a communication, and as everybody knows, because the IETF said that there's no such thing as a NAT, there are no NATs in the network, so that's actually pretty easy. What order did packets arrive in a road designation? Were they ordered? Were they modified? Were they mangled? What path did they take? How are they queued? Once you send a packet, you can put a destination address on it, and it appears at the other side, or it doesn't. It's really difficult to figure out how it got there. So we looked at this situation and got depressed about it and said, well, what would happen if we rethought the internet protocol stack with measurability as a first-class component? What if we said, well, the point of this stack is, okay, well, we have the network layer, which is hop-to-hop, and the transport layer, which is end-to-end, and each of these things had facilities in it in order to be able to answer these questions. What if answering these questions was as important as delivering packets? So the approach that we took here was to define some first principles for measurability, and then to imagine that packets could carry this measurement information. What would we put in them? So what are the candidate primitives for this? And then from the candidate primitives, follow the measurement capabilities that we would get. So the principles that we looked at were that measurement should be explicit, in-band, that the consumer should bear the cost, the measurement provider should retain control, measurement should be visible, and measurement should be cooperative. A little bit more about these. So the reason for explicitness, other than, explicit is better than implicit, from PEP 20, the Tau of Python, is that it reduces the ambiguity of the measurement, right? Like, so by using IPTTLs for traceroute, you're basically trying to do, something hop by hop that isn't necessarily hop by hop. You might not be seeing all the hops, for example. It also increases future-proofness, because if the feature is explicit, it's there for measurement. We're not going to change it for some other thing and have the measurements break. Like, so for example, stretch acts for TCP RTT. It should be in band. This is primarily to ensure that the measurement traffic is going to get treatment as close as possible to the real traffic that you're trying to measure. The consumer should bear the cost. So if you want to put a lot of boxes on path whose job it is to do measurement, and okay, well, now your throughput through those boxes goes down by 90% because you're measuring things, nobody's going to deploy them. But it's a lot easier to take that cost and shift it off to someone who's doing the later analysis. So the information that comes out of this, it's okay if it's a little bit inscrutable, as long as there's some algorithmic transform you can apply to it. The provider should retain control. This ensures that the users, so the measurement provider here in this case is the entity that's putting the traffic on the wire that has the data in it that is measurable. We'd like them to know how measurable their traffic is, right? You'd like to be able to opt out of it or opt into it. Measurement should be visible. If I can see the measurement and you can see the measurement, then everyone can see the measurement. This increases the transparency, the fact that there is measurement traffic on the wire and that that this can be trusted. And measurement should be cooperative. This is just sort of a rephrasing of principles 3 and 4. and basically to sort of leverage the existing tussle between the middle and the end. So we have a set of candidate primitives. Have a look at the paper for those. I'll be talking about timing and arrival and change detection and queue delay. So what we're not saying, hey, we should actually build all of these things into, IP version, what are we up to now? 7. Or that we should build these things into TCP2 or whatever. We're saying, this is a illustration of the principles. We're using these to test the principles and see if that makes sense. So for timing, we want to be able to figure out, what the round trip time of a particular transport flow is. Turns out that the timestamp option is almost right for this, but since it wasn't designed for passive measurement, it was only designed to give information to the sender. It doesn't expose anything about the delay, right? So if you have a timestamp or a packet that goes in one direction and then an ACK comes back, you don't know how long it took to generate that ACK. So the way that we fix this is we basically take time now and time echo. These are basically constant rate clock things, just like TCP TS opt, and then the delta time, which is this ticks in the same clock at the sender since we saw the echo. So one thing to note here is that there's a resolution overhead trade-off, right? So with respect to TCP timestamps, you have to put them on every packet because they're used for wraparound detection. For this, you could basically say, I'm going to put this on 1 over n packets, and I'm going to eat the loss in resolution. So this meets our second and fifth principles, that it's n-band and it's visible. The fact that we have this delta here is just for measurement. That meets our first principle for explicitness. And then the resolution overhead trade-off is basically a way to achieve this sender control. So the way this works, here's where it goes fast. So, okay, I send a packet with, I'll be the sender, you'll be the receiver. I send a packet with a timestamp on it. The receiver sends a packet back with its timestamp, and then it echoes back the thing. And you can see there were no delays. And I wait 2 ticks of my clock, and I send the next thing, and then we keep going and go on and so on and so forth. And if you put an observer in the middle, they can basically look at this and look at the rate of the sender's clock, the rate of receiver's clock, compare that to a local clock. I mean, you have the clock drift issues that you have anywhere where you're trying to do network-based measurement. And you can essentially figure out what the rates, the inter-departure times are, the inter-arrival times. You can get jitter out of this. And the delay information gives you the correction that you go with TCP timestamps. So arrival information, this is basically in TCP done by looking at the series of sequence and acknowledgement numbers and attempting to model how retransmission works. A more explicit way to do this would be to make this loss and reordering visible in a transport independent way. We actually didn't invent this. This is inspired by a Scott Savage paper from 1999, where this was basically trying to get better information for TCP congestion control with a misbehaving receiver. So the way that this works is you have a randomly chosen but increasing number for every packet sent. You increment it by n, or you increment it by a given increasing number, so you can tell what the order of those increases are. You maintain a running sum, and then you echo the running sum. So this meets the consumer cost primitive or consumer cost principle. Because actually teasing this apart does actually require you to look at every packet and pull things apart. So and in order to figure out what the order is, it's also explicit and visible as the other one. And we only had 3 on that one. So the way this works is you start with a starting number and you have an increment series, and we can just go through these. And in the general case, it goes back and forth and back and forth and back and forth, and you just echo the last one that you saw each time you sent it. For loss detection, let's go through this and let's say, okay, we lose that packet. Here, an observer, okay, yeah, so here you're going to basically echo back on the next packet. Well, I saw the 200 plus the 4. I saw the 204, but I haven't seen the 211, so I'm going to echo back 204. Go again. And then, yeah, so you're going to see that the, oh, wait, did I do this wrong? Okay, no. So you're going to see that the, that increment in the middle is just missing. So the sender now also knows, and any observer on the left side of the sender over here is going to actually see that that didn't get lost, even though there's no indication anywhere in this that there was a Like there's no flag on this that says, hey, this is a retransmit. You're not looking at anything in the transport level sequence numbers, so on and so forth. The observer on the other side essentially makes different inferences by looking at the series of increments. This also works for reordering. Actually, we can go through these very quickly. So here, the first packet here actually got reordered and was received after the second one. And you can again see this in the sequence of echoes. So yeah, so study the numbers and do the math for yourself offline, because I have, like 8 minutes left at this point? Less. Good. Okay. You can take this a little bit farther. There's a primitive in here called probabilistic and triggered stamping. So these section numbers are the sections in the paper. So this is essentially a request for information to be added by a router. So probabilistic stamping is, every in packets are going to get information added to the packet. Triggered stamping is you essentially have something that looks very much like the TTL time or the IP time exceeded message. You say, okay, decrement this when you are the nth router that understands this. Please put some information on the packet. And the two basic ones we will look at here were things like performance diagnostics. So, okay, I'm going to give you the timestamp for now, my instantaneous queuing delay, and my instantaneous queuing capacity. And you can essentially use this to essentially build maps of where the hot queues are in the network. You can also do this for topology discovery. So this is essentially explicit trace route. The addition that you get here is you have the AS number, some identifier that the router chooses for itself, so that if you know which AS it is, you can actually go in and look that up in a table. And then you have both the incoming and the outgoing addresses, so you'll lose a lot of the aliasing problems that you have in traceroute. So yes, we meet explicit visibility. This is an example of sort of the cooperative principle, the idea that here, okay, we actually now do need to ask the routers to do things for us. So in conclusion, measurement's critical. I think the people in the room here would probably all agree on that. This paper is kind of a position paper to spur discussion, debate, and inform protocol development that we need better support from the network. So really what we see as the main contribution to this work is the set of principles. So the idea that we have these 6 basic ideas. We can test that against measurement facilities that we look at adding not just to this imaginary future internet wherein we actually can go back and say, okay, we're going to change the stack so all of these things are built into it, but also any present sort of design for adding measurability to a protocol or for building a measurement facility that is not directly integrated with the protocol. Paper demonstrates these candidate primitives that address long-standing and important real-world measurement problems. So this is basically sort of an ad. Go read the paper. Please talk to us if you think these principles are interesting. That's really sort of the takeaway that I want to get and that I'd like you to get from this, is that we think this is a good groundwork set of principles for designing measurability for the future internet. So with that, I think I do have a little time for questions. Thank you very much. Anyone? All right, cool. Thanks.
Okay, so we're ahead of time, but maybe take a look at the paper and think more about it and come back to the Maprg list. Next is Roland.
Hi. What? No, got a clicker. Hi, my name is Ron Verhuiswijk. I work for SurfNet, National Research Network in the Netherlands, and I'm also an assistant professor at the University of Twente. This is joint work with all the organizations here on the slide, and I'm going to talk to you about the root canary and specifically about the evolution of a measurement that we started earlier this year. So first of all, what is the goal of this talk? Both I and my co-authors, Willem from NLNet Labs and Moritz from SIDN, have talked about the root canary before in various venues. But I wanted to present this at the Maprg as well because we learned stuff while we were evolving the measurement as the root KSK project sort of progressed through time and got paused at some point, which I'm going to talk about later on in the presentation. And I want to give you some takeaways of the stuff that we learned while we were setting up the measurement and while we were actually measuring and sort of adjusting what we were doing. So first of all, quick recap. Why did we start this project? I hope everybody has noticed that ICANN started this project for replacing the root DNS key with a new one this year. Anybody not familiar with this project, please raise your hand. I don't believe you, Jeff. So the goal of this project was that we wanted to track operational impact of the root KSK rollover, and specifically we wanted to see if any resolvers on the internet were experiencing problems because of this rollover process. Because at various times during this project there were going to be stages where some resolvers might start showing failures because they were unable to pick up the new key, or because they were unable to receive responses because they were unable to deal with fragmented responses coming back from the root. We wanted to do this for two reasons. We want to be able to warn people if stuff started going wrong on a large scale, but we also wanted to measure this over the whole period so we could, at the end of the process, sit down, analyze the results, and check what have we learned from this process and how are we going to have to deal with future KSK rollovers. So our measurement methodology measures from 4 perspectives, and I'm going to show you 2 of those just to explain why we think we need many perspectives. Actually 3 of those, I'm mistaken. So we use Ripe Atlas probes, which is one of the obvious choices. We use Luminati, which I'm going to tell you a little bit more about in the next slide. And we're hoping to use some of the data that APNIC collects at the end of the measurement so we can sort of compare notes and see what we observed from all of these different perspectives. And then finally, we also want to look at traffic recorded at some of the root letters, hopefully most of them. We can look at the day in the life data for that, to see what happened, what was visible from the root while this KSK rollover was going on, and how resolvers were acting based on the various stages during the KSK rollover. So a little bit about Luminati. Anybody not familiar with Ripe Atlas? Excellent. So Luminati is an HTTPS proxy service. Has anybody heard of the HOLA unblocker service? It's one of these Netflix unblockers. Raise your hand if you have heard about it. Okay, very few people. So basically, if you're in a country and you can't watch certain content on a service like Netflix, but there are other services that this applies to as well, you can sort of go through some sort of VPN service to pretend you are in another country, and then you can see the content that's made available in that country. And this is what HOLA does, but if you click agree on their terms and services, you actually agree to become an exit node for their VPN proxy service. And academics love this kind of stuff because you can use this to do measurements from a residential perspective. And this is actually something that the folks from Northeastern University who are collaborating in this project have done before, so they've used this for other measurements. They had a paper on the TLS landscape, and we had a paper at Usenet Security and at IMC, which was about DNSSEC validation. And what's really nice about this is that you have millions of exit nodes that are in residential networks. So basically, you're sort of observing the same thing that APNIC is observing with their measurement based on ads, but you have different visibility in the ecosystem. So what we do is we have HTTP requests that trigger DNS queries, and using that we were able to cover about 15,000 ASs. And the interesting thing is that 14,000 of the ASs that we covered are not covered by Ripe Atlas probes. So we are getting different visibility into the problem space, which is nice. So what is our measurement methodology? Basically, we have a set of signed records. We have signed and bogus records for all of the signing algorithms that are in use today. We have almost all of the DS algorithms that are used in today. So then you get a matrix of algorithms that you can do measurements for. And if a resolver, and we can measure one of 3 outcomes, whether a resolver validates correctly, whether it fails to validate, so it gives us a serve fail when we're not expecting to see one, or it doesn't validate, right? Regardless if it's a signed record, but the signature is bogus, it still gives us a response, so it's not validating. And of course, there are some corner cases here, but I'm not going to go into detail about those. So if you want to have a look at this project, so the URL is at the bottom of the slide. We actually have a couple of live results up. If you go to the website, you can have a look at the live results. This is for the most common signing algorithms, and this shows you visibility into the Atlas part of our measurement. Unfortunately, that's the only one for which we have live results at the moment. Luminati is a little bit trickier to get live results for that, but we're updating our results as they come in. And what you can see here, the green, so these are all pie charts. The green part of the pie chart shows you the fraction of probe plus resolver pairs that are actually correctly validating that particular algorithm and signing algorithm and DS algorithm. And the orange part are resolvers that are not validating that. So they are just normal resolvers that don't do DNSSEC. And one of the takeaways here is that you don't see any red, so we don't see any resolvers failing to validate, which is what we would expect to see if stuff starts going wrong during the KSK rollover. Now, if you click on one of these pie charts, you actually get a more detailed view for that specific algorithm. So this example shows you SHA-256DS with RSA SHA-256 signing. Again, you see the detail of which fraction of resolvers is validating and which fraction isn't. But there's also a CDF that shows you the time that the population of probes spent in that state. And the takeaway from this particular CDF, and you'll see it if you click on all of the algorithms, is that if a resolver is validating, it's actually really stable. It's validating all the time. So it never flips from validating to not validating, it's validating all the time. And that's actually a nice result because we didn't actually know this before. We didn't know if resolvers were actually stable, if they're validating, or if they flip state very often. And the resolution of this measurement is once every hour. So we think we're getting quite good visibility into this. So just to give you an idea of why it's important that we measure from different perspectives, I guess everybody sort of assumes that RIPE Atlas is somehow biased, right? It's people like us that pick up an Atlas probe at an event like this, plug it into our network. We are not representative of the internet. Residential users are representative of the internet, right? So if you compare the fraction of resolver that validate that we observe with the Luminati measurement in this case, and we compare it to the RIPE measurement, you can already see a huge difference, right? Of a set of 13,000 vantage points on the Luminati measurement, 7% were behind a validating resolver. But if you look at the Atlas measurement, then 42% of Atlas probes are behind a validating resolver. That's a huge difference. And again, the DAP measurement will give you a different number because I think it's, what is it, 15, 16% behind a validating resolver? Roughly. Yeah. So.
Sorry, can I ask you a quick question to the previous?
Yeah, sure.
Because it doesn't say InterQ, it says, can't even read it.
No, it
Gray,
says
right?
other.
Yeah,
so we didn't do the full analysis. We just looked at how many are, so the rest is either not validating or they're often non-validating, which means that they are behind one resolver that validates and one that doesn't. But we didn't do the differentiation there. You're jumping the queue. Anyway, let's go back to why we started this measurement, because we wanted to observe the root KSK rollover process. Now, the chart here shows you what that process initially looked like. And I marked one point in red, which is the first moment when we would expect that something might be going wrong. And this is September 19 of this year. At that point in time, until that point in time, we had 3 keys in the DNS key set for the root. We had the new KSK, the old KSK, and one ZSK. And on September 19, a ZSK rollover started. And that means we introduced a new key into that set. It grows in size. And consequently, this was the first point in time when responses from the root might actually get fragmented, specifically if they're transmitted over IPv6, because it would now exceed the minimum MTU for IPv6. So we wanted to know what happened. Well, I'm not even going to show you the Atlas probe results because nothing happened there. And I'm going to say something about that. So these are the number of surfill responses that we got back in our Atlas measurement. You see one little spike a few days in from the actual introduction of the new ZSK. We looked in detail at that, and that was just one vantage point failing for a completely different reason that had nothing to do with the new ZSK getting introduced. So the takeaway from this is nothing happened. This is traffic to B-root with thanks to Wes for giving Moritz access to that. The takeaway from this is, again, nothing happened because there was no noticeable increase in TCP traffic to the root, which you would expect to see because people were getting truncated responses and falling back to TCP. On the right-hand graph, you can see there's also no increase in truncated responses, so you wouldn't see TCP traffic because of that. So nothing really happened. So, wow. Summary of that, nothing exciting happened. Okay, and then, so October 11 of this year, the new KSK was supposed to go live. And then ICANN decided to pause here. Boo. So did we do all this work for nothing? Well, no. So the rest of the presentation, I'm going to talk to you about the sort of side effects that we had from this measurement and what we learned from that. So spin-offs. The first spin-off we had was an online algorithm test. While we were designing this measurement, I was having a conversation with Willem from Nelnet Labs, and we said, well, can't we use all this matrix of algorithms to actually make an online test that allows you as a user to figure out which algorithms will my resolver actually validate? And actually, that turned out to be rather easy to do. So if you go to the website, you can actually click on the test and you'll see the results. And actually for the IETF network here, so this is for my home. And I hope you can see that all the way to the right, my home resolver actually validates one of the newer algorithms, EDDSA 25519, because I run a patched version of OpenSSL to get that working. On the network here, you'll see that the left-hand column, RSA MD5, isn't treated as insecure, it's treated as secure, and that probably means that they're running bind on the network here as a resolver. Is there anybody who knows about whether that's true? Anyway, I'll ask the NOC team. The second spin-off is that we test algorithm support for all of those Atlas probes over time. So actually, if you go to monitor.rootcanary.org, you'll see a map and you'll see measurements popping up as they come in. So you'll see a little green or orange dot popping up on the map. You can click on that and that will show you the state for that resolver at that time. And it will show you a lot more, for instance, a whole table for ASs, the number of probes in those ASs with validating resolvers, whether that went up or down over time. So we get really nice visibility into the resolver ecosystem behind Atlas probes over time. And we've actually already seen that the number of validating resolvers increased over time. And I'm hoping that one day another resolver will pop up that actually validates some of the newer algorithms that we have for DNSSEC. Also, anybody have a guess which resolver these people are using? You can see that it's 192.168.1.1, but it's forwarding its traffic to somebody else. Anybody guess? Okay, it's Google, yeah. Because Google somehow thinks RSA MD5 should return a surf field. Go on, go to the next. Why is it not? Can you press? Yeah, oh, thank you. Okay, so we made a little mistake somewhere during our measurement, and actually we forgot to re-sign our test domains, and that means that the signatures were expiring. So if the signatures are expiring, what you expect to happen is that resolvers will start to return surf fields to queries that they were validating before because the signature has expired. Next slide, please. But actually something weird is happening at the top of the graph, because you see that a fraction of resolvers are still saying no error. So they are validating this and they're saying, oh, that's okay. Those expired signatures are still fine. And that's actually an interesting side effect, because most resolver implementations will have some sort of grace period, have some sort of grace period which is configurable, within which they will treat an expired signature as okay, because they're assuming that their clock is off. And from this measurement, we actually learned that that is sometimes configured to be quite extreme, and we're actually going to do another measurement later on to work out whether it's just set to a very long time or whether some resolvers just ignore the expiry time altogether, which would be bad. Next slide, please. So the final spin-off that I want to talk to you about is the Swedish canary, and I assume you're familiar with the Swedish chef. Next slide, please. So Moritz from SRDN, who is also part of this project, presented this work at DNSOARC in San Jose in September, I think. And after the presentation, the good folks from IIS came up to us and said, well, we're doing a KSK and algorithm rollover for the .SC CCTLD. And you can read more about that project on the URL that's on the slides. Slides are also on the meeting material website. And they asked if we would want to measure that and signal problems to them, because they're kind of scared. And the interesting thing about this is that it's on, I would say, a more agile timescale than the root KSK rollover, for which we now have no deadline. This is due to take place in less than 2 weeks. So they're actually starting at the end of November, and they hope to finish by the end of the first week of December. So that means that we had to work really hard to get the measurement up and running, but it also means we get our results pretty quickly. Next slide, please. So for this project, we developed some new methodology that covers issues that are specific to algorithm rollover. So I'm not going to go into details, but just to give you one example, one of the things that you need to do is you need to introduce signatures before you introduce new keys, because the RFC specified that you could otherwise do a downgrade attack. And some resolvers will actually fail if you introduce the new key before you introduce new signatures, because then it will say, I'm expecting to see signatures with this new algorithm and they're not there, so I'm going to treat this as an attack and I'm not going to validate this anymore. And because .sc was the first TLD to actually sign its zone in 2005, and this was well before the root got signed, there are still resolvers out there that have a trust anchor configured specifically for .sc. And we already experimented with this, and there's a thread on the DNSOP mailing list about this, because we discovered that most resolvers will actually prefer the more specific trust anchor for .sc, and if that doesn't match up with the key, they will return surfill, regardless of whether there is actually a chain of trust from the root all the way up until that signature that they're validating, and that's a problem. Next slide, please. So to conclude, and I think the main takeaway for me from this project is that we started measuring this root KSK rollover sort of as an ad hoc project. We had a discussion early in the year, and it turned out that nobody was actually measuring this, and then we said, well, we think this is important, so we should start measuring it. And as our thinking about the measurement evolved, lots of spin-offs developed. So we got lots of nice side results that will give us better understanding of how this protocol actually behaves in the wild. And it's also a case study of why rare events like the root KSK rollover or like an algorithm rollover that they're doing in .sc really deserve our attention as a measurement community. Because if we don't measure these things, then we're going to keep making the same mistakes over and over again. Because for algorithm rollovers, some of them have occurred in the past, and almost all of them that I'm aware of have gone wrong in some way. That's why we need to start measuring this type of stuff. So I'm going to sort of say what the chairs probably also say is measurements give you better understanding, better protocols, so fewer failures, keep measuring people. Next slide, please. Most of the data that we collect is open data. So all of the write measurements are stored in the Atlas API, so you can actually extract all of those measurements if you want to have a look at them yourselves. On the monitor.rootcanary site, there's actually a WebSocket that you can connect to, and it will stream live measurements to you as you connect to it. And all of the data sets that we're collecting will, of course, when we publish papers about this, will be released as open data. And I think that's the last. Yeah. Any questions?
Hi, this is Yoshiro Yoneya. My question is, did you analyze another root servers rather than B root server?
For the traffic for changes in traffic, no, we only had data from B routes. At some point, we will want to look at the other root letters as well, but for this particular event, we only had access, and we had to do this really quickly, right, because this is in September, and the presentation was 2 weeks later, so we had to sort of work with what we got. And I think you're now going to say that another root letter saw something different.
Yeah. So I'd like to know, there was nothing happened at the September 19th. That is a very good news for us. So I'd like to know.
Okay, so you can concur that what we saw, actually, you saw the same thing. Good. Any other questions? Okay, thank you for your time.
Thank you. Come back when you have more data about the Swedish case. Giovanni, yeah.
No, you can just wave your hand.
It doesn't
It
work.
doesn't work. Oh, you laser. Yeah, you can use laser. Yeah.
All right. So yeah, this work we conducted together with Twente and ISI. Just before I start, how many DNS people are in the room here, or the DDoS protection people? Right. So you, yeah, it doesn't work. Next, please. So in this talk, this is a paper presented in IMC last week, and the approach we have in this paper is the operator's approach. I work for an operator, and the thing I wanted to do is like how we can actually optimize and better engineer the deployments of our named servers. So this came up from a production question, and by optimizing better engineering, I refer to reducing latency to our clients because, well, time is money. So there's many reports that show that if you want to Google that, you can find Amazon saying that search times higher latency leads to loss of money, and DNS is part of that as well. So next, please. And this is the real setup we have for, it's not even working. No.
The battery's probably in.
All right. For data now, and if you're not into DNS, let me break down this to you. So we, for the DNL, the TCC/TLD for the Netherlands, we run 8 different authoritative name servers. They have this different colors. Some are Anycast, some are Unicast. You can use the same for any other domains. This is only for DNL. And we use 8. You can use different numbers. It's just for redundancy. All right, thank you. And high availability. Let's see if it works. No, all right, next, please. And when we have a client at home, let's say we want to resolve a domain name like example.nl, you go to your local resolver that you can find in a computer. Next, please. But this resolver can actually make a choice to go to any of those 8 name servers, authoritative name servers you see on top. I think it's the same if you're on here on the streets, if you want to find an ATM, and there are 8 ATM around, you can go to each of them. Some are going to be further than you, some will be closer to you. And we, as an operator, have no control on how resolvers actually get to choose. And the question that we wanted to answer is like how we, as an operator, can actually help them to get the best results, like the shortest latency to the name service. Next, please. And of course, some of the name servers, they use Anycast, which means they're like this name service distributed across the globe among various machines. Next, please. And this actually came out from observation we had at the company. So this is the same setup, but the area of the graphs show the actual number of machines that each authoritative name server has. So NetNod's a big DNS provider. They provide services for us. And you see like they have Anycast, the big Anycast cloud. But when you look next to the actual traffic, we see that the biggest name server in terms of machines that we have doesn't actually get the most traffic. And that puzzled me. I was like, how you can better engineer that? You actually see that the NS5 has a bunch of local Anycast, gets a lot of traffic, which was interesting. So like how you can actually level out this thing. Next, please. And for our Unicast sites, they're all located in the Netherlands. We have 22% of our queries comes from the US. Even though the other Anycast site, NetNod, authoritative server, has sites in the US. So what's going on here? So that when this work started. Next. And this is happening because we, as a CDN, will only operate what's on circle above. The recursive resolver. This is actually code created by different DNS software, like Unbound or Bind. And the clients actually, those clients that are located at homes, data centers, these are different people. So we have a lot of different entities, and they have different goals. So our goal is just as an operator, try to serve them better. Next. And this kind of has been done before. There was a work by Dwayne Wessos and his team, but it was in the lab setup. And our question is like, we don't want it to focus on specific software versions or vendors. We want to see how this behaves in the wild, because that's what we care about. And that's what we did. Next. So we had set up 7 measurement setup, actually Moritz did all those measurements, by the way. The same Moritz from the previous presentation. And we have used Amazon data centers. We have set up on each data center a different authoritative name server, and we have activated some of them and activated at a certain time. And next, please. So let's consider measurement. We had only 2 authoritative name servers for our example domain. And if you have a RIPE atlas, if you have only the 2 sites here, one in São Paulo, one in San Francisco, this client at home can go to this resolver, and this recursive resolver can choose what is the one he wants to send the query. Next, please. And we did have done that for all the others. So we have this combination, see like how it actually varies as you add more name servers. So the first question I had, do actually all the resolvers choose all the authoritative name servers available? Like for that now we have 8. Do they actually go to the 8 or they stick to 1? And the first thing we found is actually they use all of them. They actually query all of them. So let me give a measurement with this name 2A. It's like only have 2 sites. I don't recall by heart which it is, but what matters is like very quick. We have 96% of all the RIPE Atlas resolvers, like from all the probes, after one query, they take like less than 5 queries, like in 2 queries, to actually reach the 2 of them. And if you have like 4 resolvers, it would take like 6 queries after the first one for all the clients to reach all the name servers, which means like if you have one very badly named server, authoritative name server running, that means that this one is going to attract traffic from a lot of people because that's the way the recursors behave. Next, please. And another question we had, so we found out, okay, they go to authoritatives, but how they actually distribute the queries, because we kept on querying. These measurements were carried for every hour. We have a very short TTL, so they would expire the cache, and we would do that every 2 minutes. So let me, can you next, please? Let's consider a setup that we had. I think it's 2A. We have 2 sites, one in São Paulo and one in Japan. And what happens is like, this is the first graph here shows the median RTT for all the RAP Atlas probes towards São Paulo, towards Tokyo here. And this graph shows the distribution. If you have only 2 name servers available for this example that I know, you see that like the authoritatives with similar latency, they get like the similar number of queries. So the resolvers, like if you have more or less the same latency, I'll distribute more or less evenly. Next, please. But for sites, since RAP Atlas has a lot of probes in Europe, you would expect that Frankfurt would have a lot lower latency, which is the case, and Sydney would have a higher one. And if that's the 2 possibilities that you can go to the name servers. What's going to happen is a distribution is very inversely proportional to that. So it means that Frankfurt will actually get a lot of queries, and Sydney will going to get less. Next, please. That confirms the previous work, but for the first time here, we actually don't have done that in the wild, which is the thing very interested too. Next. Also to confirm that we have to look not only into aggregated traffic, but it's also important to look at individual resolvers, how each of them behave. It's a very beautiful picture, but let me try to explain this to you. Each column here represents one resolver, a probe, a RAP Atlas probe, and resolver. And we have divided them into different continents. So next, please. Let me focus first here in Europe. And this is the measurement. We only had like 2 name servers available in Tokyo and São Paulo. Next. We see that, and this is this is the number of resolvers, and you see some of them only stick to São Paulo here. They never distribute the queries. The y-axis here shows the distribution. So if you have only one caller, means like you only send it to GRU here. Next. It's some other resolvers, they only stick mostly to Japan here. Next. Some others, they kind of like distribute among the 2 of them. Next. And you see like 69% of all the resolvers, which is the x-axis here, they have a weak preference for one of the 2 available authoritatives. And for us, weak is just a definition like they send between 60 or 90%, between 60 and 90% of all the queries, they send to one of those name servers, authoritative service. Next. We also found that 37% of those authoritatives, and they have like what we call a stronger preference. They send like most of the traffic, 90% of the traffic to one of those 2 name servers. Next. And some resolvers, they just always choose the lowest ones available. So you're measuring the wild, that's kind of thing you would expect to get. Next. This all was done with RAP Atlas, but we also decided to look into like production name servers, and we'll look at the root name servers, use the detailed data. All the details are in the paper, and we got data there from 10 of the name servers. And this is .nl that we run. We have data from 4 of them out of the 8. And what do we see for that is the root, the queries, 60% of the queries are distributed across 6 of those authoritative name servers. So the root letters, and each color here, each band represents a server. So you see like there's an evenly distribution. Some of them are very weird here. They stick to 1. And for .nl, it's more or less an evenly distribution, which means that the production operations of the roots of the 10 letters and .nl confirms our finds of our test bed. Next, please. So what is the summary of this measurement? Resolvers will query all the available authoritative name servers, and the distribution it's inversely proportional of the median RTT of the particular authoritative to the particular resolver. And recursors will prefer a fast responder auditatives, but it cannot. But it also would query slow runs over time. There are some additional findings I referred to in the paper. You can read that there. Next, please. And that's the point, the most important point for me of this presentation, because I work for operator. We're interested in how to better engineer that. And the biggest recommendation we have here, like the conclusions that is lowest authoritative name servers, they will limit the response time of the DNS server. That means like if you have 4 name servers and one is running in a very small machine in a very poorly connected site, you're gonna reduce the performance for everybody. And if you're a global DNS provider, like we have customers from all over the world, you cannot deliver good performance with unicast. So our recommendation here is to use Anycast in all of your name servers. And why Anycast? Wes is going to talk a lot about Anycast, so you can also watch that. But Anycast, you can use the same name server and distribute across the globe in different locations, so you can provide locally better latency for all your clients. So they have to have good pairing. And based on this work, actually, are impacting production. We're actually deploying a lot of, we're replacing our unicasts and .NL for Anycast. Next, please. Next, data sets, paper, and questions.
Yeah, thank you, Giovanni. Thanks. You can, there is a question. Okay, you just take the long road.
Jeff Houston, APNIC. I'm kind of curious about your recommendation that everyone should use Anycast all of the time for authoritative name servers. How do you reconcile the issues around ICMP v6 messaging and the ambiguity and loss of signal that Anycast invariably produces? Surely that recommendation is actually not a good recommendation unconditionally, and you need to be bloody careful when you deploy Anycast in v6, because you will not ensure the integrity of any kind of ICMP packet too big signaling. So I'm sorry, it's just not a good conclusion at this point. It should be a lot more conditional than what you're pointing out.
So this work is only, I think I put in the slide, maybe I did not mention, we only have done that for IPv4, have to do that for IPv6. But regardless, the focus of this goal is to deliver better response times. And I think our conclusions still hold for that. And ICMP, this is something we have to take a look into that, but it's a part of signaling. Our goal is to deliver better performance for our clients. We want to reduce latency, so I disagree with that.
So come back with the IPv6 measurement then.
No, that's another way to see that. Well, it's something we have to do. Yep.
Okay, thank you.
Thank you.
And this is our last presentation from Wes.
Wave or shout? Wave or shout?
Yeah.
Okay. So I'm Wes Hardiker, and this is about Verfplotter, which I am not the native speaker of that language, so I'm probably mispronouncing it a little bit. Close, though. So this is about a broad and load-aware Anycast mapping study that we did in combination with the University of Twente, and I'm from USC's Information Sciences Institute. Next. Is there a clicker? Or okay, next. Oh, good. Wait. No, go back. So our goals for this project were to really develop a technique that did a few things, like accurately map Anycast catchments, and then study the B routes Anycast IPv4 catchments, and then predict some load in advance of those changes. This talk today is not about those three. Those three were discussed at the DNS OARC workshop a while ago, and you can go watch the counter talk to this one, because at that talk, I didn't talk about the study of Anycast stability over time. So today you're going to see sort of the flip side of that talk. So really quickly, as a reminder, Anycast is, a multiple sites that serve the same address or host the same address. And typically for things like RIPE Atlas or any sort of Anycast measurement utility that's been done to date, you have to have lots of measurement points. You have to lots of vantage points where you have all these devices around the net that are going to send queries to your Anycast catchment, and then you're going to watch them come back and figure out where you got to. So next. Verfplotter is sort of the inverse of that, and so we're actually using the entire internet as a vantage point. So the way we did that is we collect responses to ICMP pings that we send out from the catchment. So in the example on the screen, there's a box on the right, and you'll notice that that's within the Anycast catchment. That was a server that I ran. We sent out 5 pings, and you see them come back to different places, and we noted the discrepancy of which ones went back to which place. So it was a very different way of doing Anycast catchment. And to do all of those pings, we used previous work that was based on an IPv4 hit list. That was basically a long list of IP addresses that are likely to respond to an IPv4 ping. And it gives you a big long list of examples. That URL is later on in the slides as well. Next. So what did we see? So we studied a couple of Anycast networks, the first of which is the DNS's B-root. And you can see that this is the coverage from RIPE Atlas. So there's lots of little circles on the diagram. They're all kind of small, so to make sure that they all fit. But you can sort of see the coverage you can see a lot of bubbles in Europe, and of course some bubbles in the United States. And if you shift to our technique for doing that measurement, that you'll find that the circles actually shift quite a bit. And one thing to note is there is a huge scale difference. So I'm going to ask you to flip back and forth a little bit between the two because it's pretty. You'll notice that there's actually a fairly big scale difference. The ones on RIPE Atlas, the bigger circle size is 277 or more nodes, and on VerfPlotter, the biggest size is 185,000 nodes in one of those circles, so that there's a huge scale difference. But you can still see the shift in circles as they move from one map to the next. Okay, next. We also used, the University of Twente has a 9-site Anycast testbed that's sort of spread around the world. And you can see there's all the sites that we used for our test. Note that there are some sites that actually sort of have the same upstream, so there's a little bit of bias, toward one upstream may actually be hiding 2 sites within it because of there's sort of a single upstream. Next. So similarly, when we studied, that network in terms of what sites what IP addresses out in the world were responding to different Anycast sites, we saw sort of a similar kind of coverage where now we actually have a 9-color map. And if you go on to the next one, you'll see that the 2 things happen. One, we get more spread as we did before, but not only that, the colors actually shift. So if you toggle a little bit, you'll see that there's some places where the colors shift. Look at Australia in particular and note that the colors are shifting from one to the other, meaning that RIPE Atlas is measuring a different actually set of catchments than VerfPlotter, which is arguably more accurate. Next. So given the significant number of vantage points, what can we study and learn about networks around the internet? And so one of the things we asked is, can we study traffic catchments within an AS? Now that we have so many vantage points, can we see what happens as the number of sites change and what happens with the size of the prefixes as a larger and larger prefixes are announced, as well as what happens when the size of the AS goes up? Does that actually change visibility and how many sites are seen in an Anycast network? Next. So to answer one, this is a graph of on the bottom is the number of announced prefixes, and going up the vertical side is the number of sites. So you can clearly see that there is a relationship between the number of prefixes that are announced for a given AS is likely to mean that they are also better connected to a larger number of Anycast sites. So that gives you an indication that sort of the larger ISPs are more likely to actually deploy stuff, or more likely to hit more catchment sites. Next. This is a bar graph, so I'm going to have to walk through it because I'm sure it's quite small back there. But on the bottom right is /23s. And so what happens is one thing that we find with respect to the size, the bottom right, and if you go along to the left, it increases by 1. So it's a /23 on the bottom right, a /23 on the one next to it, 21. And it gets all the way up to a /8 in the upper left. And what we see is that the number of sites that are seen per network block increases as the prefix size goes up. So specifically, 80% of prefixes smaller than a /16 are more likely to hit a single site. And the larger prefixes like /8, /9s, and /10s are more likely to actually be reachable, to actually reach multiple sites within it. Next. And then finally, we also wanted to look into the stability of Anycast. How likely was it that things flip? So we did a study, or or University of Twente really did the study of measuring their test bed across 48 hours. So they sent these same measurements every 15 minutes across 24 hours, not 48, my bad, to their tangled site. And a couple of things about this graph is that the to NR and the from NR graphs are in the middle, and note that there's a definite break because the top line is 3.5 million on average, and the bottom line is about 4,000. We'll get to that in a second. And in the middle is measurements that went to not reachable or from not reachable. So in other words, in the middle of the study, all of a sudden that site went offline and the pings went away, or inversely, all of a sudden that one came in. Next. So a couple of things to note about this is that 3.54 million VPs, maintain catchments. In other words, over the 24-hour period, we never saw them flip, at least on 15-minute interval. 89,000 actually did change from either from responsive to non-responsive or vice versa. And then 4,600 vantage points, which is 0.1%, actually changed catchments. So in other words, these are people that started off in one catchment point and then at some point ended up at a different site. The interesting thing to note, though, is that you could actually look at this and argue, well, it's actually more likely that they're going to turn their computer off than they will actually switch catchment points, right? But the reality is they probably turned their computer off intentionally, and they probably didn't flip catchment points intentionally. That's the network, making fun of it. But the end result is only about 1 in 1,000. Only about 1 in 1,000 chance of a TCP connection lasting longer than 15 minutes will actually switch to a different Anycast site. Next. In all of that data, so now if we just look at the ones that did flip, it turns out that 63% of the ones that flipped came from 5 ASs. And so these are the top 5 flipping ASs. And I'm sure you've noticed that the top one is 51%. So ChinaNet alone accounted for 51% of the things that flip. And I think that's the way that they do their network, and they have a special network over there. So they do some load balancing tricks that probably are the result of that. Of all the flips, they're all located within 2,809 ASs out of the total set. Next. So really quickly, sort of the summary of why we think that this technique is actually a better mechanism for measuring a large quantity and being able to really study Anycast network. I've given you some of the results, but in the end, VerfPlotter sees about 430 times more network blocks than Atlas. But interestingly enough, Atlas still has some unique ones, like somebody else was talking earlier about 2 different ways of measuring stuff. Atlas still saw some unique blocks that we didn't see. For example, they saw 2,079 that we didn't see, and similarly, VerfPlotter saw some that Atlas will never see in certain countries that Atlas can't really be deployed in. And everything we did, by the way, was /24s because that was the sort of the smallest routable address block that you typically see in IPv4 on the internet. In total, VerfPlotter, one sec, go back. In total, VerfPlotter saw about 3.8 million different /24s. Note that VerfPlotter doesn't have everything geolocatable. There were some address blocks that we actually don't have geo-IP data for, whereas Atlas, because the probe IDs are actually encoded with the location that they deployed at, they actually have 100% coverage, so that's actually a better thing. All right, next. And then finally, this technique and the code and the data sets are all available for you to use. So if you want to pick up the code and go, if you have an Anycast network and you're interested in using it, please come talk to me because we'd love to see this run on more stuff to see more data out in the wild. And with that, I'm done. Questions?
Robert Kishtakir, IPNCC. Can you go back one slide, please? Thanks. Could it be that RIPE has 2,000 or so unique /24s? It's because the target list, the hit list that you had for pinging, included an address in that 24 that was not pingable. So you thought that there is an IP address, but it didn't respond, so then you consider that you didn't get data from that.
Yeah, I mean, the reality is that in some places, the firewall restrictions are very different, right? They don't allow any incoming
Reality
ICMP.
is there.
Yeah, right. So we haven't been able to analyze exactly why there's that much difference, but the reality is that people can go plug those devices in behind a network where maybe that entire country doesn't allow incoming pings, right? So there's boundary issues on the flip side as well.
Definitely. Somewhat related, what stops you, at least as an experiment, to do a full IPv4 ping? Like John Heidemann, in this case, does that like every 24 hours or something. So
yes, and so he's a co-author on this too.
Yeah.
The reason being is that with a hit list, you don't need to flood the internet. So you could. You're absolutely right.
he does. He floods the internet every 24 hours. So what's one more ping?
Right, and we use his results in order to make it slightly easier for us to send out that many. You're right. You can't. Absolutely.
I'm only arguing that maybe doing it once would give us somewhat better results. And then if it turns out to be a useful thing, then maybe repeat it. But
possibly. I'm not sure we want to do it for like the 24-hour, 15-minute study, because we actually did rate limit them going out, so that actually doing the entire hit list that we did took me 15 minutes a run from when I was doing it at Beirut, because we didn't want to oversaturate the network with people.
No, that's absolutely fair. I'm not saying that you should over-execute direct one, but the tools are ready to do that.
Yeah, no, you're right. It's possible. Okay, any other questions? One more.
Giovanni Saidian. I was not involved in the study, but I know the people, but it's just not a question, it's just a comment that I had. So first time I saw the presentation and the paper, I was like, this is interesting. How can I actually, as an operator, use that? And I was talking to John about that later. And I think as an operator, the cool thing about this FairFloat is actually, if you want to design your own anycast system, you can actually get your prefix, your anycast prefix, and before putting it in production, you can actually say, hey, I'm going to have some sites here and there. What's going to be the load distribution? So it's just a remark for people here. If you're designing your anycast network, if you want to like sort of estimate where the traffic is going to go, to which sites, you should use this tool, because we're going to use that.
And if you watch the DNSO ARC talk, that's exactly what we did. Is we actually were able to predict load at Beirut in advance of actually switching over, so we could figure out that. And the results were, always forget which one is which, but we predicted either 82.6% would still go to LAX and the rest would go to Miami, and the measured result was 81.4. So they were either 0.1 and 0.4 or 0.6 off. I mean, they were really, really close. So it was an accurate prediction mechanism, but go watch the OARC talk for that half.
Yeah, great work.
So, okay. All right, thank you.
So quick question. Are your data available somewhere? Or
Yes, the data on the next slide.
Okay, so I missed that. Sorry.
Yep, the data sets are all there. The paper's there, and it was an IMC paper, so it's just published a week ago or 2 weeks ago when at IMC. And the software is there too, so it's very easy software to use. You just say ping and it does. Give it a hit list.
Okay, thank you very much. That means we're at the end of our agenda, and we have 4 minutes left. Wow. So you can either leave the room, or you can also ask additional questions or whatever. I don't know. Thank you very much. See you next time. Thank you very much.
Yeah, you're welcome.
I hope you had a good experience here on the chair.
Sure. Oh, you're the chair on the chair.